Since 1952, the primary tool for classifying human cognition has operated under an epistemological limitation. Diagnostic manuals, like the DSM, rely on mapping observable behavioral projections. They take the continuous variation of the human mind and force it into discrete categorical boxes defined by symptom checklists and duration thresholds. By categorizing at the surface level, this approach collapses distinct generative cognitive systems into identical behavioral labels. It simultaneously fractures similar cognitive architectures across different diagnostic categories because their surface-level reactions to stress appear varied. Observable behavior is a low-resolution shadow. It provides a data point on what is happening, but it lacks the resolution to model the underlying architecture generating the response. Reported diagnostic overlap reflects these shared behavioral regions within a continuous space. Homorbidity is the expected mathematical outcome of projecting a complex manifold onto a flat set of labels. As long as clinical psychiatry classifies at the level of behavioral projection, it will struggle to map the true generative architecture of human cognition. The Receiver Parameter Classification System, or RPCS1, offers an alternative framework for this assessment. RPCS1 shifts the target of assessment from discrete disease models to continuous parametric cognitive configurations. It replaces the behavior equals label heuristic with a generative model. Behavior is the output of a receiver, whose stability is a function of both its internal architecture and its environment. In this model, R represents the internal receiver architecture, the specific tuning of the brain's processing variables. S evaluates the stability of that receiver when subjected to external environmental conditions, E.
Cognitive variance exists as a continuous mathematical landscape, where adaptive stability dictates human function. Mapping this generative architecture requires starting at the mathematical bedrock of the framework, the Information Manifold Model, or IMM. The IMM assumes that all theoretical informational states form a structured mathematical space. This is the informational manifold, denoted as M. This illustrates the system's intrinsic flow. Vector fields pull informational states towards stable attractor basins. However, observers cannot access this full manifold. We only see a subset through a projection map. The multidimensional reality of cognitive processing compresses into a flattened, observable state space. This projection is mathematically lossy. Fine structural details of the cognitive manifold are removed to create the coarse representations used in observation. This lossy projection suggests that analyzing the shadow of behavior alone results in an incomplete understanding of the underlying system. Projected signals are processed by the brain's internal machinery, the receiver, modeled as a parameterized dynamical system. Every receiver is defined by 5 primitives: temporal integration, signal gain, filtering threshold, update elasticity, and adaptation rate. Rather than binary switches, these parameters operate as a continuous, tunable system. High temporal integration, or TI, allows an individual to deeply process and accumulate context over time. This frequently results in a delayed response time. High signal gain creates sensitivity to fine environmental details, though it also amplifies background noise. These dials follow the principle of parameter coupling, where their interactions produce specific behavioral regimes. Pairing a delayed integration window with amplified signal sensitivity creates an oscillatory dynamic.
The system experiences deep processing while being simultaneously reactive to immediate stimuli. Human neurotypes are coordinate configurations within this continuous 5-dimensional receiver space. To determine whether a specific receiver profile remains functional under stress, we use the stability function. This is the formal RPCS1 stability potential equation. It demonstrates how internal structural parameters interact with external forces. The critical external variables acting on the receiver are H, representing environmental entropy, and P, representing time pressure. This equation illustrates environment-receiver mismatch. A receiver that is stable in a low-entropy environment can destabilize if the environmental entropy increases. The model defines pathology as a transient dynamical state triggered by environmental forcing, rather than an intrinsic property of the brain. RPCS1 formalizes the ask of assessment as an inverse problem. The inverse problem involves predicting the hidden internal receiver parameters, R, strictly by observing behavioral output, B. Within a specific environment, E. Relying on a single environmental data point produces a blurry cloud of statistical uncertainty, leaving receiver parameters underdetermined. It cannot distinguish between different architectures producing identical outward behavior. Introducing multiple environmental contexts maps these changes under pressure, resolving the cloud into a precise coordinate. This suggests that multi-environment sampling is a mathematical requirement for accurate assessment. Without it, the observer cannot differentiate between stable traits and environmental reactions. We can apply this framework to clinical presentations by viewing them as continuous attractor basins. The rigid/freeze regime is a structural state often categorized under the umbrellas of autism or OCD traits. In this regime, critically low update elasticity paired with high filtering locks the receiver into processing loops that resist modification. Contrast this with the overload regime, an unstable state found across various diagnostic spectrums. Overload occurs when input density exceeds processing capacity. Signal-noise discrimination fails, leading to behavioral shutdown or chaotic responses. Traditional diagnostic systems often cluster these behaviors based on the visual symptom of the shutdown itself. RPCS1 indicates that these similar behaviors can be generated by contradictory parameter combinations. Addressing the behavioral presentation of overload without calculating the underlying parameter coordinates provides an incomplete diagnostic picture. We can examine this through a case study of two subjects who both exhibit severe behavioral overload. Subject B represents a high reactivity profile. Their overload is driven by high signal gain and low filtering. Environmental noise enters their processing without being attenuated. Subject A represents an oscillatory profile, also presenting with behavioral overload. Their architecture is different. They combine high signal gain with exceptionally high temporal integration. These charts show that as environmental entropy increases, both architectures fail, triggering an overload state. Subject A requires deep processing time, but is interrupted by high-gain sensory input. Subject B lacks the filtering threshold to block out rapid background noise. Human processing functions through continuous receiver configurations. To achieve stability, clinical focus must shift from labeling a behavioral projection to mapping the underlying manifold.